In this video, we're going to start taking a look at nuclear reactions. So first off, a couple pieces of terminology. In all chemical reactions, not just nuclear reactions, we always have what we call the reactants, which are the things that are reacting, written on the left side. And the products, the things that they turn into, written on the right side with an arrow pointing from the reactants to the products to indicate that the reactants are turning into the products. In the context of nuclear chemistry, the reactants are usually some isotope and the product is some other isotope. And we often refer to the reactant as the parent and the product as the daughter. So this is specific to nuclear reactions. The parent isotope is the one that you're starting with, and then the daughter isotope is the one that it turns into. So whenever we're dealing with chemical reactions, one thing that we need to keep in mind is that reactions must be balanced. So what that means is that the total mass of all of our reactants, total mass of our reactants must be equal to the total mass of the products. So remember, if we're using our nuclear symbols that we learned in the previous video, our total mass, the masses were all represented in the superscripts, in the number up on top. So the total mass is just going to be the sum of the superscripts. So essentially, if you add up all of the top numbers on the left side of your reaction, it has to equal the sum of those top numbers on the right side of your reaction. We also need to keep the total charge equal. So the total charge, aka that bottom number, the subscript of our reactants, must equal the total charge of the products. So this is also shown in our nuclear symbol, where our charge, or our atomic number, if we're looking at a nucleus, is the subscript. So the total charge is just the sum of the subscripts, or the bottom numbers, in our nuclear formula. So in addition to the nucleus of an atom, so there are several other types of particles that frequently appear in nuclear reactions. And they're all listed up here along with their symbols. So protons, neutrons, and electrons are things that should sound familiar to you, and things that you already know some things about. Note that electrons are sometimes also referred to as beta particles, and we'll talk more about that in future lessons. But for now, be aware of that. Is another thing they're called, and sometimes changes the way that they're symbolized. So for a proton, looking at our symbols here, the top number, remember, is our mass, the bottom number is our charge, so this should make sense to us. We know that a proton has a mass of 1 atomic mass unit and a charge of +1. So same system for our symbol here, and we use a lowercase p to symbolize protons in these types of symbols. Or a proton is also the same thing as the nucleus of a hydrogen atom. A hydrogen 1 atom, hydrogen with a mass of 1 isotope, is just a proton. So you will sometimes see, rather than the P for proton, this written as hydrogen. Either one is fine by me, take your pick. For a neutron, we have a mass of 1 and a charge of 0. Again, that's consistent with what we know about neutrons. We use a lowercase n to symbolize neutrons in this type of system. Electrons, mass of 0, charge of -1, also consistent with what we know about electrons. We use a lowercase e or the Greek letter beta. Again, take your pick. They both symbolize the same particle, and it doesn't matter which one you use. These other things may or may not be new to you. Positrons are probably new. Maybe you've heard the word in passing. But a positron is essentially just a positively charged electron. It is a particle that has negligible mass, effectively 0 mass, like an electron, but differing from an electron, it has a +1 charge instead of a -1 charge. So the symbol reflects that here, mass of 0, charge of +1, and we can either have E or beta here. So the symbol is very much recognizing that it is like an electron, but it has a +1 charge. So we see that distinction in the subscript. Then we have alpha particles and gamma rays. Alpha particles are a helium-4 nucleus, so we can represent them either using the atomic symbol for helium, which is He, or the Greek letter alpha, because they are also called alpha particles. They contain 2 protons and 2 neutrons, so that gives us a total mass of 4 and a charge or atomic number of 2. And then gamma rays are actually not particles, they are just energy, which is why they have neither mass nor charge. So they have a mass of 0, they have a charge of 0, and then this little squiggly thing is the Greek letter gamma. It's sort of like a Y, but where the vertical part is like a little loop instead of just a line is usually how I think of drawing it. I usually do kind of a loop-de-loop this way sort of situation. So we see these types of particles in lots and lots of nuclear reactions, and we want to be able to write nuclear reactions such that they are balanced. So let's take a look at an example together, and then you can try one on your own. So if we take a look at an example I've mentioned previously, that carbon-14 turns into nitrogen-14, we can kind of fill in the blank here for what else must be produced in order for this reaction to be balanced. If a reaction happens, it must be balanced. So what we're looking for is for the total of all of our subscripts on the left to equal the total of all of our subscripts on the right, and the total of all of our superscripts on the left to equal the total of all of our superscripts on the right. I usually figure out those numbers first and then try to figure out what symbol matches them, what symbol, what letters to put based on the numbers that we find. So looking at this example, we consider our superscripts first. Highlight my invisible superscript here. We currently have 14 on the left and 14 on the right. So we need for these two superscripts to add up to this one. They already do, basically, which means that our superscript, our mass for this particle has to be 0. The only way that the sum of all of our superscripts on the left and right can be equal is if the missing one is 0. On the bottom, we've got a 6 over here, a 7 over here, and then a blank to fill in. So again, we need these two things to be equal. We need 7 plus mystery number to equal 6, which means that this mystery number must be -1. So if we think about what particle has a mass of 0 and a charge of -1, consult our list here, we find that that is consistent with an electron, so we can put an E here or a beta, your choice. And that would balance this reaction. So when carbon-14 turns into nitrogen-14, an electron is also produced in that process, or a beta particle, however you want to think of it, is also produced in that process. So one more example. Figure out a mystery reactant on this one. So we're looking for what parent isotope reacts to produce radon-228 and an alpha particle or helium nucleus. So you can take the same process that we just talked about, and why don't you pause the video here for a moment to try to figure out what that missing reactant is that balances this reaction. So once again, we are looking for, oops, wrong writing utensil, for the sum of the superscripts on the left and right to be equal. So on the right side we have 228 and we have 4. Those two things added together gives us a total of 232. And then we're looking for our subscripts also to add up to the same number on the right and the left. So we've got 88 and 2 on the right, which means our missing number down here must be 90. So this, in this case, is what we're going to use to go find the symbol that goes with this. Those numbers are not consistent with anything on our common particles list. Generally, if you have a large charge or a large atomic number, it's an element. So you want to go look up the element symbol on the periodic table. So if we go and find atomic number 90, atomic number 90 is thorium. That has the symbol TH. So we would put a TH there to represent that element.